So, if you think back to the big journey that we went on in Chapter 2, we spent a lot of time learning what a derivative was, but once we got there, our goal was fairly straightforward. We wanted the ability to, if given any function, take its derivative. And what we learned is the way we're going to take derivatives is really dependent on what the function itself is. If the function's basic enough, the derivative's easy enough. But when functions got more complicated, we had to learn these additional rules. Things like the chain rule and the product rule and the quotient rule. And that made finding derivatives significantly more difficult. In Chapter 3, our journey is kind of analogous to what we did in Chapter 2, except now we're focusing on antiderivatives. And since antiderivatives, loosely speaking, are just kind of undoing the derivative process, what we need to learn in Chapter 3 is how to undo all those different rules that we learned in Chapter 2. Undoing the more basic rules like the power rule isn't that hard. But as we saw in the last section, undoing the chain rule was really difficult. We have to learn this technique called U substitution, which is probably the single most important technique for integration, for finding antiderivatives. However, it's not the only technique for finding antiderivatives. And in this section, we're going to learn another technique. The technique we're going to learn in this section is what's called integration by parts. I'd argue, although it's a bit subjective, that integration by parts isn't quite as important as U substitution, but maybe it's the second most important rule that you learn for integration. And unlike U substitution that undoes the chain rule, integration by parts is going to undo the product rule. What am I talking about? Well, first let me remind you of the product rule. If we were trying to take the derivative of x squared e to the x, we can't just take the derivative of the x squared and multiply that by the derivative of the e to the x. The derivative of a product is not the product of the derivatives. We have to use the product rule. And the product rule tells us that we're going to take the derivative of the first thing, the x squared, and then we're going to multiply that by the second thing, e to the x. And then we'll add to that the derivative of that second thing, so the derivative of e to the x. And then we'll multiply that by the first thing, which was the x squared. So when I take the derivative of the x squared, I get 2x, and then I leave the e to the x alone, so my first term is 2x e to the x. And then when I take the derivative of e to the x, well, the derivative of e to the x is just e to the x, so I get e to the x times x squared, or x squared e to the x. The derivative of x squared e to the x is 2x e to the x plus x squared e to the x. And you're like, yeah, I know that. We learned that like a month ago. Right, but I'm going somewhere here, trust me. What if I asked you to evaluate the indefinite integral of 2x e to the x plus x squared e to the x? Think about if this is something you'd be able to do. If you saw this in a different context, you might be like, I don't know, maybe if I used a clever U substitution, because U substitution feels like this super powerful method that works on all sorts of crazy integrals. And while it's true that U substitution is a really powerful method, I don't think it'll help you in this specific problem. And you're like, yeah, I wouldn't have done that. What I would do is I'd recognize that you're asking me for the antiderivative of exactly this same expression that you just got as your answer when you were taking the derivative of x squared e to the x. So if the derivative of x squared e to the x is 2x e to the x plus x squared e to the x, then the antiderivative of 2x e to the x plus x squared e to the x is just x squared e to the x. What I'm saying is this answer right here is just x squared e to the x, and then I guess technically for the nitpicky types out there, I should tack on a plus c. And that's entirely correct. That's the right answer. However, there's kind of a problem with that answer. Would you have been able to recognize that if we hadn't just done this work in red? Right, I did this work in red for a reason, to try to make this problem doable. But what if we hadn't just done this problem? Could you have recognized that? And some of you are like, no way. And some of you might be like, well, kind of. I mean, I was pretty good with the product rule, and I can kind of see the different parts of the product rule here. I think I might have been able to recognize that. It's like, all right, for those of you that are like the superstars that think you might have been able to recognize that, first off, that's really impressive, and I believe you. But secondly, I could mess with this a little bit. Like, I could recognize that each of these terms have an x e to the x in them. So I could factor out x e to the x from both terms, and then over here I would be left with a 2, and over here I would be left with an x. And what I'm saying is I could rewrite this question in a slightly different form that would be a lot harder to recognize that expression could have come from a product rule if x squared e to the x is what you put into the product rule. The point that I'm making is this question is the same as the question in blue, and I doubt you'd be able to answer the question in blue by just kind of seeing the product rule in this integrand. And hopefully by now you're like, all right, I believe you. There's a purpose you're teaching me integration by parts. Go ahead and do it. Okay, well, integration by parts is going to undo the product rule. So as a reminder, this is the product rule, right? This is one way to write the product rule. If we have a product of two things, like x squared and e to the x, and we're trying to take the derivative of that product, what we do is we take the derivative of the first thing, multiply it by the second thing, add to that the derivative of the second thing, multiplied by the first thing. So this is a true statement. And because this is a true statement, because the derivative of this side is equal to this, the antiderivative of this side must be equal to this. Right? If the derivative of f times g gives me this, the antiderivative of all this must give me f times g. But this is not integration by parts. And the reason why is because very rarely are you going to be asked for the antiderivative of something that just so happens to fit this form so perfectly. It's fairly uncommon that what we'd end up with is exactly what's written in red right here. So what we do instead is we take advantage of some more basic antiderivative rules. What I have on the right side of this equation is the antiderivative of something plus something else. So I can rewrite that as two separate antiderivatives, right? The antiderivative of f prime g plus the antiderivative of g prime f. And then what I'm going to do is I'm going to get this term all by itself. So the way I'll get this term all by itself is I'll subtract the antiderivative of f prime g from both sides of the equation. So if I subtract this from both sides of the equation, on one side of the equation, I would just have the antiderivative of g prime f, this thing right here. And on the other side of the equation, I would have the f times g minus this term that I subtracted from both sides. So the antiderivative of f prime g. This right here will end up being your integration by parts formula. However, nobody writes the integration by parts formula this way. For whatever reason, people don't use f's and g's in their integration by parts formula. In place of all their f's, they use the letter u, and in place of all their g's, they use the letter v. I'd argue that u's and v's are kind of the worst possible choice of letters to use because they look really similar, whereas at least f's and g's look pretty different even if you have bad handwriting. But for whatever reason, this is what people are going to use. They're going to change all the f's that you see into u's and change all the g's that you see into v's. And we're actually going to go one step further. Instead of writing u prime in place of this f prime here, we're going to write the primes with the letter d. So instead of writing f, I write u. Instead of writing f prime, I write du. Think of the d as representing the derivative of this u. Similarly, instead of writing g prime, I'm going to write dv. This might seem like a strange choice of letters and symbols for us to switch with when f's and g's and f primes and g primes work perfectly fine. But this choice of letters is going to work out pretty nicely when we actually implement this algorithm. Kind of for the same reason we made the choices that we chose for how we write u substitutions. We're making these choices for a reason. So trust me, I'm not just trying to change letters to mess with you. Let's rewrite this statement using these translations. So I'd have the antiderivative of, and then instead of g prime f, I would write dv and u. I'm going to write the order u times dv. The f is the u and the g prime is the dv. The antiderivative of u dv is equal to f times g, so u times v, minus the antiderivative of f prime g, which is du times v, although the order I'm going to write it in is v du. The antiderivative of u dv equals uv minus the antiderivative of v du. This is your integration by parts formula, and it's something you're going to want to memorize. It kind of, I don't know, maybe just to me, sort of rolls off the tongue if you say it enough times. It almost seems like a song or something. The integral of u dv equals uv minus the integral of v du. Write it down the first few times you need it, say it a few times, and before you know it, you'll have this memorized. But you do want to memorize this because this formula will be the key to integration by parts, and integration by parts is a really important integration technique. So it's something that I want you to take beyond this class, which is why I want you to memorize it. I bet at this point you're like, wow, that's a lot of letters and a lot of deriving stuff and telling me to memorize stuff without really showing me any work. What do you say you do an example? I'd love to. Let's finish this video with one example using our integration by parts formula, which I copied right down here, and show you how it works. What you'll see when we work through this example is this formula doesn't really answer the question. It doesn't tell you what the integral of u dv is. It rewrites that integral as a different integral. So really the key to integration by parts is you take a problem that's really hard, you run it through this formula, that leaves you with another problem, but that problem is a little bit easier or more manageable. and then we figure out the antiderivative of that. So this formula doesn't take care of the antiderivative, it just changes the antiderivative into something that's more doable. Let me show you an example. Suppose you were asked to find the antiderivative of x cubed times the natural log of x. What you see here is something times something, which won't always tell you should use integration by parts, although in the integration by parts section, you're always going to be using integration by parts. But generally, when you have something times something, it's a good idea to think integration by parts, especially in the instance where a u substitution won't really help you. I mean, if you stare at this and you're thinking u substitutions, your u for your u substitution would either have to be x cubed or natural log of x, and neither one of those is going to produce a du that's going to be really helpful. I don't think u substitutions would help at all, so maybe integration by parts is the way to go. For integration by parts, our integration by parts formula has a u and a dv on the left side of the equation here. So what you want to do is look at this thing and figure out which of these two terms is u and which of these two terms is dv. Making that choice will be kind of the hardest part of integration by parts, just like choosing u is the hardest part of u substitutions. But for now, let me show you it both ways. Let's be like, I have no idea which one of those terms u should be and which one dv should be. So let me try it both ways. If I choose u to be equal to x cubed, then what I'm left over here with dv is natural log of x dx. Conversely, if I chose u to be equal to the natural log of x, then what I'm left with over here is x cubed dx. At this point, we don't know which of these two methods is going to work out, but as I tried to kind of harp on in substitution, sometimes you don't know in calculus, and you just have to try different ways until you find something that works. So where do we go from here? Well, if you look up at your integration by parts formula, we have the u and the dv, but what we're missing is the du and the v. I like to write the du below the u and the v above the dv, and I'll explain why in just a sec. But the point that I want to make is we have u, we need to figure out du, we have dv, we need to figure out v. The way we're going to figure out du is the exact same way we figured out with u substitutions. So maybe as a reminder, when we were doing u substitutions, we'd first figure out what u would be equal to, and if it were x cubed, we'd then figure out the derivative of x cubed, and we'd write it as du over dx is equal to 3x squared. And then after that, our third step is we'd kind of treat this like a fraction, and we'd multiply both sides of the equation by dx and get du is equal to 3x squared dx. When we first learned u substitutions, we did this as 3 different steps. But quickly we learned that we didn't need this second step, right? We could just write u equals x cubed and then jump down here to du equals 3x squared dx. What we're going to do with integration by parts is identical. The first line here says u equals x cubed. We're going to cut out this second line because we're experts thanks to all the work we did with u substitutions, and we're just going to write du is equal to 3x squared dx. Similarly, if we were doing this the method in red and we had u equal to the natural log of x, we'd write du is equal to 1 over x dx. Easy enough? Alright, let's move on to the v's because those are a little bit more tricky. The idea for the v's is we're supposed to think backwards. This line right here is analogous to this third line that you see right here. I have dv equals natural log of x dx, and I want to think about what the first line must have been to get me there. Well, let's see. From this third line, if I go back to the second line by dividing both sides by dx, I get that the derivative is whatever's written right here, 3x squared. So to get back to the first line, what I have to do is take the antiderivative. The point is, v is the antiderivative of dv. So over here in red, when I have dv equals x cubed, what would have allowed me to write this as my third line is if I had that v was equal to 1/4 x to the 4th power. Make sure that checks out. If my first line said v equals 1/4 x to the 4th power, my second line, if I were to write it, would say dv over dx is equal to 1/4 times 4x cubed. In other words, x to the 3rd power. And then my third line, I'd multiply both sides by dx, and I'd get that dv is equal to x cubed dx. The point is, my third line is x cubed dx. My first line should have been v equals 1/4 x to the 4th, just like I wrote right here. I have all the pieces that I need for integration by parts over here on the red side. What about on the green side? Well, maybe you see that there's a problem over here. We don't know what function, when you take its derivative, gives you the natural log of x as the answer. And you're like, yeah, we do. 1 over x. Nah. The derivative of 1 over x is not the natural log of x. The derivative of 1 over x is negative x to the negative 2 power. The derivative of the natural log of x is equal to 1 over x, but that's not what we're trying to figure out here. We're trying to figure out the antiderivative of natural log of x. We want to know what function, when you take its derivative, gives us the natural log of x, and we don't have an answer for that at this point in the class. What does that mean? It means that we must have chosen incorrectly over here the green way. When we're using integration by parts, we can't make u x cubed and dv the natural log of x dx, because if we do, we get stuck when we're trying to figure out v. So this way is not going to work. This must be the correct way to go. Where do I go from here? Well, remember your integration by parts formula. Your integration by parts formula says that the integral of u dv is equal to uv minus the integral of v du. Let's fill in all the pieces. The integral of u times dv. U is the natural log of x. dv is x cubed dx. Oh, nice. The exact question that I'm asking right here. X cubed times the natural log of x. X cubed times the natural log of x. That is equal to u times v, so the natural log of x times 1/4 x to the 4th, minus the integral of v du. So 1/4 x to the 4th times 1 over x dx. This thing that was the original question, I have written as a different expression. If I could figure out the right-hand side of this equation, I'd have the answer to the question and I'd be done. Let's see if we can clean up the right-hand side a little bit to make it more doable. First, we have this 1/4 x to the 4th natural log of x. Great news about that. There's not an integral symbol out in front of it. This is done. There's nothing else we have to do with this. Our work left to do is over here. Over here, we have a 1/4 that's a constant, so I can pull that out in front of the antiderivative symbol. So I got minus 1/4 antiderivative of x to the 4th times 1 over x. But x to the 4th times 1 over x is the same as x to the 3rd power. I cancel this x with one of these x's. And that's great news, because what I've managed to do is rewrite this integral that I didn't know into this integral that I do know. I could take the antiderivative of x cubed, no problem. What I would do is use my power rule. I'd add 1 to that exponent, and then I'd make sure that I put a 1/4 down in front so that if I were taking the derivative, it would cancel that 4 out, and I'm done. I guess I could tack on a plus c if I want to be really nitpicky, and I could even clean this up a tiny bit. But this expression doesn't have any integral signs written in it. I've got my answer. As always, if you wanted to check your answer, you could take the derivative of this and make sure that it brings you back to where you start. But just know that typically what happens in these is when you take the derivative, you get kind of a big mess, and then you have to be really careful with your algebra. You have to make sure that you cancel out things just right if you want to get back to what the original integrand was. Integration by parts is kind of a cool technique. The challenge with integration by parts is twofold. First off, you have to see that you need to use integration by parts, and that'll take a little while. But that's not anything we have to worry about right now, because we're in the integration by parts section. So every problem that you see here, you'll know that you need to use integration by parts. The second challenge is properly picking u and dv. And we'll get a lot of practice doing that, but often the best way to go is just try it both ways and see what happens. And I know that might seem really frustrating. You're like, no, I don't want to waste my time trying it the wrong way. But I'd argue that it's not a waste of your time. Because if you do a problem like this where you make dv the natural log of x, you'll realize that that's not going to work because we don't know the antiderivative of natural log of x. So the next time you see one of these and you're trying to decide what u should be and what dv should be, you won't even think about the option where dv is the natural log of x, because you will have already eliminated that possibility from the work that you did when you tried to make dv the natural log of x. So much like u substitution is something that you can really only learn through repetition. Fortunately, what we're going to do for the rest of this section is just repetition. The next video will just be a whole bunch of examples. But let's save that for the next video.